Okay. So heat engine and refrigerator are opposites, and we derived this and this. That's all. Okay, that's all we have done in the last class. Okay, today, so we studied first law of thermodynamics in the last class. Okay, so today we will be studying something called second law of thermodynamics. Okay, so what second law of thermodynamics says is there are different statements for second law of thermodynamics. Okay, but basically what it says is, can anyone tell me, sir, you said this is the efficiency, and unnecessarily I'm sending a lot of heat to the exhaust pipe, right? That is what is your Q2. So did anyone think, sir, why should I even send that much of heat, right? Why can't I try to, take as much as heat in the engine itself so that by the time the exhaust is coming out, it is already very low temperature, which means all the heat is already taken inside the engine itself, right? And the answer is what second law of thermodynamics says is, so what I'm trying to ask you is, sir, why can't I make this Q2 0 so that I don't lose any energy to the exhaust at all, which means Q1 by Q1 will become 1, which means the efficiency will be 100%. Why is it not possible? Well, we have done, in the past 200, 300 years, they have done so much of research to increase the efficiency. They are trying to keep on increasing the efficiency as much as possible. But nobody has come up with an engine where you can have 100% efficiency. Meaning, if I put 1000 joules of petrol, 1000 joule energy of petrol, I'm not going to get 1000 joules in my car wheels. Always there is going to be some heat lost in the exhaust, and that is what second law of thermodynamics says. So take it down.
The second law of thermodynamics is basically Zurich's law, right?
Say that again. Second law of thermodynamics is,
This, the name starts with Z. I'm not sure what the full names are.
another name for second law of thermodynamics is there are two different statements. One is called Kelvin Planck statement. Okay, we'll come to that. You see, I've been drawing this again and again. Okay, it's so important. So the question is, sir, why can't I make this Q2 0? Why can't I just, whatever is coming in, why can't I, make it into, convert it into work? And the second law of thermodynamics says that it is not possible. So take it down. All heat is your hot reservoir. All heat absorbed from hot reservoir cannot be converted to work. There will always be some heat lost to the sink. Sink means you are dumping something, right? So in the kitchen, why do you call it a sink? Because you are dumping the vessels. So similarly, here you are dumping the heat. So there will always be some heat loss to the atmosphere. Okay. Again, this is a law. Okay. I don't think we have a proof for this, but it is what we are observing all the time. Okay. You can improve the efficiency, but you cannot completely make it as 100%. Okay. So in other words, okay. So since this is talking in terms of engine, right? This statement was given by Kelvin Planck. So that's why it's called Kelvin Planck statement. So take it down. Any question? Anything not making sense? Only if you study along with this diagram, it will make sense. Okay. The book sometimes, they would have given this separately. Okay. You have to study along with this diagram. Anybody still copying? Can I change the screen?
Yes, sir.
Okay. Now let us go to the heat pump. So what did we say at the beginning? Heat will always flow from higher temperature to lower temperature. You know that this is air, higher temperature, 25 degrees Celsius. This is lower temperature, let's say, ice or freezer. Okay. So what this statement says is, unless I give some work, I cannot pump this heat out of this lower temperature. So if I keep the ice, obviously the ice will melt. Why? Because it is taking the heat from 25 degree to 0 degree. So the heat will always flow from higher temperature to lower temperature. But if at all I want to make the water go from my ground level to the second floor, then I have to use a motor or pump. Okay. Motor is the electric motor, but then that will be connected to a pump and that will be spinning and then that will be pumping it will be creating, as it's rotates, it will be creating some vacuum. And based on that vacuum, the water will be rising up. Okay. And that is what we are pumping. So similarly, unless I give some work, I cannot make this heat to go this way. Okay, that's what the second statement. So take it down. This is also second law of thermodynamics. This was given by a scientist called Clausius. So we call it as Clausius statement. I don't know if this is what Kirtan you are trying to say. Is it Clausius which you tried to say, or?
Yes, sir.
Okay. It's very simple. Okay. Heat can never flow from flow from lower temperature to higher temperature. To higher temperature. Without giving some external work. Here, what did I say? Q2 can never be 0. If Q2 is never 0, this efficiency will never be 100%. Okay, same thing over here. W can never be 0. Okay, here also you could have taken it down. So take it down properly. Q2 cannot be 0. Okay, so that's why this will become 1. So efficiency cannot be equal to 1. Okay, either you can say 1 or 100%. Because 100% is 100 by 100, which is 1. Similarly, I'm going to say here, what did I say in the equation? I got something like if I say W cannot be 0, right? If this cannot be 0, this can never be infinity. So we say that beta can never be infinity. Okay, so both the statements within second law, you have two different statements. One is Kelvin Planck based on heat engine, and another statement, Clausius statement, which is based on heat pump. Okay, and within that statement, there are two ways of understanding. Okay, either you can say W cannot be, equal to Q1. In other words, Q2 cannot be equal to 0, or you can say efficiency cannot be 100%. Here you can say W cannot be 0, which means beta can never be infinity. That's all. Okay, very simple. Okay. Whatever we observe in the nature, they are given it as a statement. First law of thermodynamics and second law of thermodynamics. Okay. So let's come back to first law of thermodynamics. Okay. Let me show you where we are in the handbook. My PDF. Okay, I don't want to wait for my PDF to open. Let's see. Q minus W is equal to delta U. This is what is first law of thermodynamics. This we studied in the last class. Can anyone remember what is this law based upon? Nobody knows anything.
Law of conservation of energy.
Law of conservation of
Energy.
okay, very good. So it's basically based upon law of conservation of energy. Okay. I cannot give 1000 joules of energy from in petrol and expect 2000 joules of energy in the wheel. The first process we call it as cyclic process. So take it down in the handbook. I may not have shown you the steps, so please take it down properly. Suppose if you consider pressure and volume, let's say you're starting from state 1, this we call it as state 1. If you have particular pressure 1 and volume 1 and temperature 1, this is state 1. If I come to something like, state 2, which is P2, V2, T2. Suppose if I make some other process in such a way that it's coming back here. Okay, this is what is called cyclic process. Why? You started with state 1, you went to state 2, and then you came back to state 1. So if you come back to the same point, the energy is still going to be the same, right? So that means, everyone listen carefully. If you have any doubts, please open your mouth and clarify your doubts. Let's say I start, I'm having some 5 joules of energy. Due to some state change, due to some temperature change, let's say, I lost some temperature, which means temperature dropped to some 25 degrees Celsius. It dropped to say 15 degrees Celsius. Or let's take it as 35 to 15. By some other process, again, I'm taking it back to 35 degrees Celsius, which means a change in energy, right? Here, let's say I had, say, 20 joules of energy. Here, let's say I had 10 joules of energy. So when it comes back, because of the temperature increase, again, it will be coming back to 20 joules, which means the delta U will become 0. Why? Because U2 minus U1. But then in this case, final point and initial point are same. Okay. Okay, let's see. So because of this, this will become 0. So Q minus is equal to delta U. So based on this theory, I know delta U is 0, which means Q minus W is equal to 0, which means to say that Q is equal to W. Okay, so take it down properly. In the handbook, I may not have given all these steps. Page number 33. Okay, I've just given you only the hints. If you know this, handbook will make sense. If you don't know this, handbook will not make sense. Anybody still copying? Can I go to the next one? The next one is isolated system. What do you mean by isolated? There are two types of interaction, right? When you have a piston like this, and if you have put it on the stove, right? Listen carefully. Um, when I'm giving heat, right, only Q is entering in. There is no mass entering in, right? But if it is like an isolated system, it will be completely like a flask, thermo flask. So it will be completely insulated. And this is what we mean by completely isolated system. Okay. There is something called mass transfer and energy transfer. Here we are doing only energy transfer. We are not sending more gas. We are just increasing the energy of the gas. Okay. So here also you have some gas, but something like your flask, right? Thermo flask. Let's say it's completely insulated, which means heat cannot go in. Heat cannot come out. Heat cannot enter or exit. Okay. If I say heat cannot enter, what does that mean? Q is equal to 0, because Q is what is the letter we are using for heat energy transfer. Q is equal to 0. So coming back to our usual formula, Q minus W is equal to delta U. Okay. So what do we know? For isolated system, Q is 0. Here delta U was 0. Here Q is 0. When I heat this up, listen carefully. The piston is moving upwards, which means work is done. But here, is there anything moving? Is there any piston to move? There is no piston at all, right? So it means work is also 0. Okay, in this system. That means this will also be 0, which means to say that delta U will be 0. What does that mean? There is no change in internal energy, because if you put some hot water inside the flask, even after say 3 hours, it's still going to hold all the energy. That's why it is, you are feeling the heat, or the water is still hot. Copied?
Yes, sir.
So we studied cyclic process, we studied isolated system, right? Now let us study some other thing called isothermal process. It's a very important one. Any guesses? What do you mean by isothermal? Is that such a difficult one? Iso means same. Thermal means temperature. So that means same temperature.
Q is equal to W.
Yeah. Why? If the temperature is not changing, what can you say about the internal energy? Is it going to change?
No, sir.
No, which means same temperature, so same internal energy. Remember, I'm not saying internal energy is 0. I'm saying change in internal energy is 0. So that means this will become 0. So what this means is Q is equal to W. These are all called ideal processes, okay? Meaning for our ideal case scenarios, right? We can say that this will be the case. Let's talk about one more process called isobaric process. Any guesses? What is this? Bar means
Pressure.
pressure. So that means same pressure. Same pressure between two states, right? But go back to the basics. What did we say? This is pressure and this is volume. So if the piston is moving downwards, when the engine is pushing when the petrol vapor is pushing the piston downwards, the pressure will drop, whereas the volume will increase. Initially it is here, but then by the time this piston is moved downwards, I thought of sending you some simulations, I forgot. Okay. So I need to make a note somewhere to send some simulations for you. Just a sec, let me make a reminder. Or if you want, you can search for engine simulation in YouTube. Okay. Maybe after discussing this, we'll go to that. I'll show you some videos, the class itself. It's very interesting to see that. So when the pressure is pushing this, it'll be coming down. So you see the volume has increased, whereas the pressure will decrease. Initially, the pressure is high, but then it has come down here. Okay. And I told you the work done is given by the area under this. This is the basic. But now what they are saying is it is isobaric. So isobaric means 1 and 2 will be in the same level. Sir, is it possible for you to do this? Well, there are some, as I told you, it's ideal cases, right? So we'll talk about this. W can be written as P into delta V, right? Pressure value into delta V. Length into, sorry, this is your length and this is your breadth. So the area under the curve, or I should write as work is equal to area, which is equal to this value, this height into breadth. So pressure into delta V. This is U. So that's all. You cannot do any simplification because you don't have any zeros here. okay, like what we had in the previous cases. So you can stop here, or if you want, some books will show that this is coming on this side. So P into delta V plus delta U. Okay, what other process I can think of? Isothermal, isobaric, same temperature, same pressure, anything missing? Can we say same volume? Okay, so that
What about
means,
isochoric?
yeah, that is same volume. Okay, so there is a process called isochoric.
For that final equation is delta U is equal to Q. So
Okay, let's see what you're saying is true. Isochoric means same volume. Same volume means, listen carefully, pressure is here, volume is here. So you're going from here to here. In isobaric, you went this way. Isochoric means same volume, so which means you're going this way. But what is work done? Work done is area under the curve. So is there any area below this line? Area means you need a width also, right? If you don't have a width, you will have only a line. So you cannot calculate area for a line. That means work done is pressure into delta V. So same volume is delta V is 0. So that means, yeah, work done will become 0. Very good. So that means if I come back to my first law of thermodynamics, W is 0, which means Q is equal to delta U. What does that mean? If I keep, so very important, take down these diagrams properly. You know that if I put it on a stove, what will happen? These air molecules will get more energy and it will start pushing the piston upwards. But what if I put a stopper over here? Then what will happen? As you heat this up, whatever heat you are giving, that will get converted to internal energy. You're unable to imagine what I'm saying, because no energy is lost in work. Can anyone tell me where do you apply this? Every day we are using this in one of the application. Anybody?
a car tire basically, can we say, for this it's a pressure cooker.
Yeah.
But another example which I was thinking was like tires.
Yeah.
Tire.
Tires.
Tire keeps rotating, temperature increases, pressure also increases, but the volume, like the size of the tire, still remains the same.
Okay. But don't you think depending upon the temperature, there will be a small change in volume also, because it's going to expand in summertime, very hot temperatures.
So,
Yeah.
if you take the normal road cars which we are driving currently, I don't think the volume increases. But if you take race cars, in those, because of temperature and more driving, in that the volume changes.
Okay. So yeah, it's possible. Okay. But the increase in volume is going to be very, very negligible. So what you are saying, I can accept it. But maybe in a race car, you are going to be going at a very, very high speed, which means the temperature rise is going to be extremely high. Is that what you're trying to say? So since the friction is
Yes,
going
sir.
to be higher, the heat is also going to be higher. Yeah. Okay. In that case, I think the pressure will also increase slightly and the volume will also increase slightly. But a better example would be pressure cooker in this particular case. Why? Because the moment you put some rice and water, right? The first thing what you do is you put the lid and then you close it. What does that mean? Even if I put it in the stove, right? You have some water or some rice particles here, right? So the internal energy keeps on increasing, but this lid does not lift up, which means the volume remains the same. Okay, so take it down, very important. So since the volume is same, work done is 0. So what is the meaning of this? All energy supplied is used to raise the internal energy. As there is no energy lost in work. Given out as work. Since all the energy is given directly, this is equal to this is 0. Any questions, any doubts?
No, sir.
So we studied isochoric, isobaric, isothermal, okay? And then cyclic process and isolated. So what is remaining? Let me check. I see adiabatic is remaining. Yeah. So let's talk about
Adiabatic is one.
adiabatic.
Diabatic and adiabatic, sir.
Yeah. If I keep dia is the root word for through. Can anyone tell me why do you call it as diameter, a circle? Because it is passing through the, what is this? Everyone sleeping? Hello?
Yes, sir.
Hmm?
I'm not sleeping, sir.
Okay. What do you mean by diameter? It has to pass through the center, right? If I
Yes,
keep it
sir.
here, it is not a diameter. So only if it passes through the center, anything which is passing through the center is called diameter. Similarly, when I say diathermal, the meaning of this is heat can pass through it. Okay. But if I said adiabatic, it is opposite of this, which means no heat can pass through the surface. Okay, so do you understand the word dia and then I think there is a word called diathermal or dia. Do you have any words, any other words that comes to your mind? Somewhere in biology we'll study diather. Diaphanous. Do you come across the word diaphanous? Anything like that? No? Okay, I don't remember. There are some words. So whenever you see dia, it means it is passing through something. Okay, so here it is passing through the center. Adiabatic means heat cannot pass through the surface. Why am I able to heat this? Because this surface is diathermal. Okay, but what if I keep something like an insulated cylinder here? Pay attention, this is very important and it will be confusing. So this is what is your insulated. So whenever it is insulated cylinder, you have to show it like this. So you have some gas here. And this piston can also be like metal piston, right? Which means heat can be going through the metal piston. But then I'm going to assume that this is also insulated. But still the piston can move up and down. Okay. So listen carefully. Heat cannot pass through it. Okay. And this is what is called a adiabatic situation. Okay. But then I can pull this out. Okay. Either I can pull it out or I can push it down, which means I can do some work. Would you call this as isolated or not? I cannot send any heat, right? From outside, it cannot go in. From inside, it cannot come out. So can I call this as isolated system?
Yes, sir.
Well, the answer is no, sir. Okay. The reason for that is if you go back and check your isolated system, did I show any piston? Can you do some work here in this container?
No, sir.
No. And that is what is insulated, right? Q is also 0, work is also 0. You see, no piston here, which means I cannot do any work. I cannot transfer any heat. That's why everything becomes 0. Okay. Something like your thermal flask. But here, this is not a flask. Okay. It is almost like a flask, but then you have a piston on the top. Okay. So that means only since the heat cannot pass through, the Q alone will become 0. So apply your first law of thermodynamics. Q minus W is equal to delta U. So you said Q is 0. You agreed that Q is 0 here, which means W is equal to minus. Either I can write as minus W is equal to delta U, or you can say W is equal to minus delta U. What does that mean? I told you if I'm pressing the piston inside, right? It is work is negative because I'm doing work on the system. So take it down properly. Work is negative when work done on the system. Whereas this W, when I'm pulling it out, right? It is something like your expansion. Okay. Of course, here also I am trying to do the work, but then, if I imagine that it's something like, pulling it out, like, piston moving up, then work is done by the system. Okay, let me finish this first. So what this means is, when I compress this, what do you think will happen to the gas molecules? Anybody? Will it increase the temperature or decrease the temperature when I compress this?
Increase the temperature.
Increase the temperature. Very good. So that means the internal energy, will it increase or decrease?
Increase.
Increase. Very good. So that means, take it down properly. When you compress it, right, W is taken as negative. Okay. And as you compress it, okay, maybe I should write, when you compress it, temperature increases. So delta U will also increase. U will increase, which means delta U will be positive. Okay, why? Because U final minus U initial, so this will be positive. But then when you compress, I told you W is negative. You see, this is the meaning of this. Okay, when this is positive, when this is negative, right, this value will be positive. Let's say I compressed it for 5 joules of work. Only when you put some numbers, it will make some sense. This minus is there in the formula. So minus, but then I said I'm compressing it, which means it is minus 5 joules. Bit confusing, so please pay attention. This minus is there in the formula. This W is negative. Negative compression means negative, which means delta U. So delta U is positive. Minus into minus, it is positive. So for the internal energy would have increased by 5 joules because no other heat is lost outside or no other heat is coming inside, which means delta U is plus 5 joules. What do you mean by plus? Internal energy has increased. Another situation is something like, expansion. So take down all these diagrams and notes properly. Okay. All these things are not given in your handbook. Suppose if the temperature is suddenly dropping, right? So what will happen here is, let me see how I can explain this. The temperature suddenly drops. Of course, it is all insulated. So it's completely insulated, which means adiabatic. Okay. But when I'm pulling this piston outside, W is positive. Okay, so it's something like expansion. So expansion is usually taken as positive. So when I pull this out, what will happen? What will happen to the gas temperature? Will it rise or will it drop? Hello. When you compressed it, the temperature raised. When you expand it, right? When you pull it out,
Increases.
the temperature will actually decrease. It will decrease. Okay. The reason for that is, instead of say 1 meter cube, let's say you are pushing this out to this level, which means volume increased. When the volume increases, the pressure will drop. When the pressure drops, temperature will also drop because pressure and temperature are proportional. Okay. And if you're wondering, sir, volume is increasing, so don't you think? So this is like, how do I explain this? So when you pull it out, the pressure is dropping. And since the pressure is dropping, the temperature will also drop. But volume, what's happening? Initially, the volume is dropping. Sorry, volume is increasing. So when volume increases, okay, that ideal gas situation, we will talk about that because, you know, when I say P and V are inversely proportional, you should keep the temperature constant. Here, the temperature is not constant. Okay, let's try to explain it later. Let me not confuse you right now. When you expand it, pressure drops, so temperature drops, so internal energy drops. Okay, if you don't know what these letters means, then you cannot study thermodynamics. So that means delta U, what do you think? Will it be positive or negative? From the initial state, the final state is having lower value. So U final minus U initial. So I'm saying the final temperature is lower temperature. Say this has become, say, 5 degrees Celsius, whereas initially it was at 25 degrees Celsius. Okay. Sorry, this is energy, so I should not talk in terms of temperature. Okay. So since the energy is dropping, this has to be negative. Any doubts around following this?
Yes, sir.
So minus W is equal to delta U is what I told you. Minus is there in the formula. This is positive work. Let's say I'm doing 5 joules here. Let's say I'm getting 5 joules of work. So which is positive. So the delta U will be plus into minus. It will be minus. That's all. So here when the W is positive, this is negative. That's all I'm trying to say. Here when the W is negative, delta U is positive. Okay, unless you have these diagrams, this is definitely not explained properly in your textbook. So a bit confusing. So take it down properly. Okay, so your homework is page number 33. Completely study this from your handbook. Okay, and go through your textbook also. So we studied second law of thermodynamics, 2 different statements, and then we studied different processes: cyclic process, isolated, isobaric, isochoric, isothermal, adiabatic. Okay, so thank you all. If you have any doubts, stay back. Otherwise, you are free to go.
Thank you, sir.
Thank you, sir.
Thank you,